Okay, so welcome to week 8 of our live discussion session, and today we'll discuss sequential estimation. Okay, and right. So just a small note from the last class that so in the last class e to the power minus I theta. So we discussed how this is derived. So I just want to clarify this again. So in the Euler's form, e to the power minus I theta is represented as cos of minus theta plus I sine minus theta, right? And if you see this, so minus theta will actually lie in the fourth quadrant of the axis, and in the fourth quadrant our cos is positive and the sine is negative, right? And so that is why cos of minus theta becomes cos theta, whereas sine of minus theta is minus sine theta, right? So that is why e to the power minus I theta is represented as cos theta minus I sine theta. So this is a clarification which I wanted to make from the last class. Okay, so sequential estimation. So what is sequential estimation? So far we have seen that we have a batch of data y1 to yn, and we are trying to estimate the parameter from a batch of data, right? So at every time instant, do we require to process on a batch of data? Okay, so we don't need to do that, right? So every time we don't need to you know uh, process a batch of data and compute a new estimate. So what we can do is that we can just update our estimate as every new observation comes, right? So rather than processing every time processing on a group of data, and the group of data keeps increasing, so we are now going to see how we can just sequentially update our estimate. So our signal model still remains y at any time k is h times xk plus vk, where vk is our AWGN noise, which is Gaussian distributed, right? So for n symbols, and we have seen this now many times. So you have y1 to yn, which is your this is my observation data which we observe, and h is my uh, parameter which has to be estimated. X is my pilot symbols, and this is my noise samples, right? So this is represented as a vector y is h times vector x plus vector v. Okay, and we saw this in the previous classes that this estimate h hat, it comes out to be x transpose y divided by x transpose x. Now what is x transpose y? And we discussed this. So if you have x transpose y, so say you have a x vector, which is say some x1, x2, so on up to xn, and say you have a a y vector y1, y2, so on yn. So if I multiply x transpose y, then I will be getting summation of all x k and yk, right? Product of sum. And similarly, x transpose x will be basically summation of uh, xk squared. Okay, so this is you can just note that this is the estimate at time n, right? So this is, say, you can say h hat at n, that is after n symbols. If you have, so if you process n symbols, then we get h hat of n as given in equation 1. So let us also define what will be my variance of error in the estimate, and that from our previous classes we know that if I denote it by rho of n, if I denote rho of n as my error in estimate, then that is sigma square over uh, x transpose x, basically, which is given as shown in equation 2. Right now, what we need, so we have till time n, we know what is my estimate, okay, and what is the variance of error of my estimate. Now, how will the now at time n plus 1, do we again need to perform all this sequential batch processing again, or do we not need to do this step? So we are going to see what to do at time n plus 1. So yn plus 1 will be h times xn plus 1 plus vn plus 1. Okay. This is our signal model, and h hat n plus 1. So here now k will go from 1 to n plus 1. Similarly, a denominator also k will go from 1 to n plus 1. So this is my old method. Right. If we employ the old method, then if we do this, then we'll get the answer. But we don't want to do this, right? We don't want to do this kind of iterative method. So what we can do? So now if I break this into two parts, so we'll get k is from 1 to n xk yk plus xn plus 1 yn plus 1, right? So it is the same meaning. If I number this as step 1, this is as step 2. Similarly, the denominator can also be broken. K is 1 to n x square k plus x square of n plus 1. Right, so we are separating out the n plus 1 term in the numerator and in the denominator. Okay. Now, if I say this is step 3, so now what we are going to do is, so we are going to use the fact that h hat n. What is h hat n? So this is summation k is 1 to n xk yk divided by summation k is 1 to n x square k. Right, this is what we have. So if I use this expression of h hat n, so if you see, I can replace this term, summation xk yk. I can replace this by h hat n summation x x square k, and note here k is 1 to n. Any confusion in this step? And my x n plus 1 y n plus 1, it remains as it is. Okay. Right, and I'm not touching my denominator in step 3. Now in step 4. So now in step 4, what we are going to do is we are going to so here we have two terms, right? So we have, this is a term 1 and this is my term 2. So in step 4, we are going to add and subtract x square n plus 1 minus x square n plus 1. Okay, and my term 2 remains as it is. So I'm not touching my term 2 again so far. Okay, and then in step 5, what we'll do is, now we are going to open the bracket. So if you see from step 4 to step 5, right? So here, if I take in step 4, if I club the first two terms with h hat n, then the numerator and denominator cancel out, and so we are only left with h hat n in step 5 as the first term. Okay, and then in the second term, we have h hat n minus x square n plus 1, okay, which is my second term. And my third term is x n plus 1 y n plus 1. And so this is step 5. If anyone has any doubt, you can feel free to ask questions. And in step 6, now what if we see in the second term, if I take out x n plus 1 as common, then we have y n plus 1 minus h hat n into x n plus 1. So we have this. So this term in the second term is my error term. Okay, this is represented as e n plus 1, and I'm not changing my denominator yet. Okay. So now what we are saying is that this that the term which is remaining Okay, so this term which is remaining of the second term, we are denoting it with another variable as k n plus 1, which is defined as the gain at time n plus 1, right? Okay. Any confusion? Now we are going to use again the our original formula, that is h hat n is summation xk yk divided by summation xk square. So this was the the old method, and similarly the error estimate was sigma square over summation xk square. So these are the formulas which we were using so far, and if we use that, we'll get this gain term. So this is my gain at t is n plus 1. So we'll get this as x n plus 1 rho n over sigma square plus rho n x square n plus 1. So what we can say is that h hat at n plus 1 is basically h hat of n, right? So this is my estimate at time n plus the gain at n plus 1. Now what is the gain at n plus 1? This is the gain at n plus 1, right? So if I name this as equation 3, so if you see, this is gain at n plus 1, and this is my error, prediction error at t is n plus 1. So now I don't need to again do summation overall xk yk divided by summation overall xk square. So now I just need to keep my h hat n. Okay, I need to store my h hat n in my memory, and h hat n will be updated to h hat n plus 1. And so we are simplifying the computation, and that is why this is a sequential update equation, right? So we just need to keep track of the previous estimate of h hat, which we computed, and we'll use that previous estimate to compute the next estimate, right? So it is like storing an intermediate value, and we don't need to store the first value, right, which we require. So this is called the update equation, and this update only requires yn plus 1, right? That is observation at n plus 1, which you will have x n plus 1, that is the pilot vector which we will be sending, then rho n and h hat n. So these four quantities you require to compute the new estimate. Okay. Any doubts in this update equation? Okay. So now we are going to see how the error variance will be updated. So far we saw how our estimate is being updated. Now we need to see how is the error of my estimate being updated, right? So we were using the notation rho n, right? That is error update till time t equal to n, right? To find out what is my error update. And now rho of n plus 1 will be basically sigma square plus k is 1 to n. If I again now separate the denominator plus x square of n plus 1. Now what is the first term in the denominator? Right. So this term can be represented as sigma square uh, divided by rho n. Right. So if you just go back to the formula, we have sigma square rho n is basically sigma square divided by summation x square k, right? And this is still k is 1 to n. So we are just playing with the fractions. And if we solve this, right? So if I take so rho n will get multiplied with x square n plus 1, and rho n will go to the numerator. And if I further solve this, then we get, say, this is step 1, step 2, step 3. Okay, so in step 3, if you see, we have rho n x square n plus 1 divided by sigma square plus rho n x square n plus 1. right? So what is this term? This term is nothing but my kn plus 1, which was my gain equation. Right? This is nothing but my gain equation, which you are getting. That is why our rho n plus 1, that is my this. So my estimate error update is nothing but 1 minus kn plus 1 xn plus 1 into rho n, right? So this is how my error variance update is happening. So if I summarize, we have h hat n plus 1, which is h hat n plus kn plus 1 times en plus 1. So this is my gain equation and this is my error equation. Now here kn plus 1 is given as shown in 2, right? So this is xn plus 1 rho n divided by sigma square rho n x square n plus 1. And our error is shown in bullet 3. So this is yn plus 1 minus h hat n xn plus 1. And finally, we have the rho n, which is we require. So this is as shown, right? So just using these 4 equations, we can solve any problem, and we'll see when we'll solve the problems. So any questions or clarifications till here? Anyone? No? Right. So, okay, I just wanted to introduce the Bayesian or MMSE estimation a little bit, and then we'll solve the problems of sequential estimation. Okay, so what is the Bayesian framework of estimation? Right. So far, what we were doing is that we have a signal model, y is h plus v, right? And h is the desired parameter which has to be estimated. And so far we were considering that our parameter was not random in nature, right? So it was deterministic in nature, and this was an assumption which we were taking. So for instance, what we were saying is that this is my h, right, which we are and this is being influenced by additive noise, and we are getting some variations which is my y, and these are being sampled as y1 so on up to yn, and we were using these samples y1 to yn to find out the h. So basically my h was deterministic, right, and it was not random in nature. So far in the entire analysis till week 7, we saw that h was not random in nature, and but now in the Bayesian framework, right, or the MMSE estimation, our parameter to be estimated is going to be a random variable itself. Okay? So we have the random noise and we have the parameter itself, which is random in nature. So we are going to see how to estimate the parameter in such kind of scenario. So let us consider n sensors. Okay, so assume that say there is a air pollution monitoring system, right? Say there is a air pollution monitoring system. So say you have a entire city, okay, and say you have different sensors which are located all over, and they're all the city, and they are trying to measure the air pollution at their end. And what they will do is you have the central server, and they will send their data which they have sensed to the main server, right? And it can happen that some of the sensor is not accurate, whereas some sensor is accurate, right? And so if you consider this, say y1 comes from sensor 1, like sensor 2, sensor 3, so on up to say sensor n. So y1 is say sensing the parameter h plus having some noise v1. Similarly, y2 h plus v2, and so on yn is h plus vn. Right. So each sensor is sensing the same parameter, but is being influenced by the additive noise differently. Okay. Now we need to estimate h from these n noisy observations which we have. So it's kind of a wireless sensor network, and you are sending all your sensor information to a cloud server or some centralized location, and you want to process the parameter there, right? So how to do, uh, and now the challenge with us is that the parameter which we want to estimate is also random in nature. So earlier we knew that the parameter was deterministic, it was not random, but now the parameter is also random. So what to do in such a case? So earlier we were, if you just remember, we did the the maximum likelihood estimate, right? So we used to take the log of the likelihood probability, and we used to maximize it, and we then further proved that the maximum likelihood is equivalent to the least squares error estimate, right? So the MSE is equivalent to the least squares error estimate. But now, so we still have, this is our likelihood probability, right? That is probability of the vector y, that is my observation y given the parameter h. But now we have an additional term which is the probability of h itself, right? And this probability of h is called the prior probability, right? This is called the prior PDF, which exists. Okay, and this is, so what we're saying, that underlying parameter is itself random in nature. So the MLE estimate which we were doing so far, so now this MLE estimator won't work. It won't work in this framework, and now we need to develop a new estimator to incorporate the prior probability or the prior distribution of the parameter. Okay, so I'll again take you to the famous Bayes rule, right? So what does the Bayes rule say? That, so it says that probability of h given y, it is probability of y given h times ph divided by py, right? So if you see these terms, so the numerator is likelihood times prior, right? So what is the Bayes rule saying? So you have the a posterior, that is the probability of h given y, and that is the likelihood, which is probability of y given h, multiplied with the prior probability, right, which is p of h, and divided by p of y. So p of y is it's just for normalization, so we can ignore it uh, for the time being. So in the MLE, what we, so in the MLE, pH did not exist. Like there was no concept of prior probability. So we were saying that maximizing the a posterior is equivalent to maximizing the likelihood. Okay, so this was the concept which we're using, but now maximum likelihood does not exist because we have a prior also. So now we need to maximize the a posterior probability, that is probability of h given y, right? And in fact, we are going to derive that the estimate of, that is the estimate of h, that is h hat, is actually coming out in terms of the posterior, right? So what is my aim? Okay, so we want to estimate h hat, which is a function of the observation, right? So my estimate of the parameter is actually a function of the observations, and we are going to use the likelihood probability, right? This is my likelihood, and this is my prior probability, that is p of h, and we are going to use these two probabilities, and we are going to estimate the h hat of y. So what is my cost function? Okay, what is my cost function? So like earlier, we were maximizing the likelihood, right? Maximizing the log of likelihood, which was our cost function. We used to differentiate it with respect to h to find out the optimum value of h. So now if we see, so we have the estimation error, which is h hat of y minus h, right? This is my h hat minus h is my estimation error, and we are squaring it. Why are we squaring it? Okay, that's it. That is one question which you can have, and then we are taking its mean, right? So we are going to do three things. We are going to first we want to minimize the error, that is h hat minus h, right? And yeah, any question? Okay. So we want to minimize h hat minus h, right? And if we square it, then the problem becomes a convex problem, right? What is a convex problem? So, a convex, so you have a curve, right? And it has a single minima, right? Single minima. So that is a convex problem. So it is always easier to, solve quadratic functions, that is which are of the power 2, right? So we want to, that is why we are squaring it, so that it becomes a convex function, and then we can easily differentiate it and solve for the optimum h or the minima of the convex function, right? And we are taking the mean over what we are, since you know that since my h is random variable now, so we need to average out over all the, over the PDF of h, basically that is over the PDF of my parameter, and that is why we are taking out the expectation also. So that is why this is called the mean squared error or the MSE. Okay. All right. So just note that now we have h and y are uh, dependent on each other. Okay, they are not independent to each other, right? So that is why there will be a joint PDF between these variables. Okay. So how do we? So this is our mean squared error, right? So this is expectation of h hat minus h squared. So now we have two random variables. One is dh and one is dy. So my first integration will be with respect to h, right? So we want to eliminate all kinds of randomness which is happening due to h, and then we want to eliminate all kinds of randomness which is happening due to y, right? So we will have two integration. One first will be dh, the second will be dy. Okay. Now the joint PDF, okay, is basically my conditional PDF multiplied with the marginal PDF, right? So ph given y times py. So here we have the joint PDF, and if I break the joint PDF in as the conditional times the, the marginal PDF. So if you see, we have basically two integrals, right? We have the inner integral, right? In the inner integral, what we are doing is that the squared error is being averaged over all possible values of h, right? Over dh for a fixed y. Okay, so for a given y, we are averaging first over all h, and then what we'll do is we'll then do dy. Sorry, yeah. Then we'll be doing py dy, right? So for a fixed y, right? MSE for a fixed y. So for a fixed y, we have the inner integral, right? This is my inner integral. Okay, and how will we solve this? So to solve this, we need to differentiate it. So we are going to differentiate with respect to h hat. So del by del of h hat. And if I differentiate it, so just note that this probability of h given y, it does not depend on h hat. And so we differentiate it. And if you solve this, so h hat y ph given by dh. And so basically, if you solve, you take the negative to the right hand side and it becomes positive. And if you equate it, so what we'll basically get is that h hat of y is basically expectation of h given y, which is basically integration of h ph given y dh. And what is ph given y? So Yeah. And what is pH given by? This is the a posterior probability. So if you just again recollect the base rule, that is probability of H given Y is probability of Y given H, pH over py, right? So basically what we are having is that H integration of H times the a posterior dH, right? So this is so basically what we see that for a case when the parameter itself is having uh, a random uh, PDF, in that case the expectation of the posterior uh, probability is basically the estimate, right? So any questions up to here? No, no doubts. Right, so we'll then go to problem solving. Is the question visible?
Yes, sir.
Okay, thank you. Thank you. Okay. So yeah. So we have a sequential fading channel estimation problem. Okay, and our output is given as yk is h times xk plus vk. And we are given the x is 1 minus 1 1 transpose is my pilot vector, and n is 3, that is we have 3 observations, and y vector is -1 4 2, so this is my uh, observations. So n is 3 and these are the 3 observations which we have, right? And at n plus 1, okay, and it is given that at t is n plus 1, okay, x4 is -1 and y4 is 3. Okay, these are all given. Now basically here's first it is asked in the question that what will be h hat of 3, that is at n equal to 3, what will be my estimate. Okay, so just note that while this is a sequential estimation problem, but to note to calculate h hat 3 we need h hat 2, right? And to calculate h hat 2 we need basically h hat of 1, right? So since for the first part of the question we don't have h hat 1, we don't have h hat 2, so that is why we are going to apply the standard procedure, that is x transpose y divided by x transpose x, right? This was our estimate, and this will be up to n, this will be up to n equal to 3, right? So if we solve this, so we have x transpose, so you have 1 minus 1 1, and this is being multiplied with -1 4 2, so this is x transpose y, and x transpose x is basically 1 minus 1 1, and this is multiplied with 1 minus 1 1, right? So you have x transpose y over x transpose x, and if you solve this, you are basically going to get -1 minus 4 plus 2, okay, divided by, you have 1 plus 1 plus 1, right? So what we have is -5 plus 2 divided by 3. So we have -3 divided by 3, which is -1. So the answer is -1, which is h hat of 3. That is estimate at uh, the third time instant. Okay. Any doubt in this question? No doubts. Right. So now we have the same problem which was given in the previous problem, and the question has asked what is the prediction error, okay, at time instant n+1. Okay, let us solve this. So just to recollect, what is the prediction error? Okay, what is prediction error? It is en+1 is yn+1 minus h hat n x of n+1. Right, this is my prediction error formula. So E4 will be y4 minus h hat 3 into x4. Okay, and what is y4? Okay, so y4 is given as 3. It is given in question that y of 4 is 3 minus h hat of 3 we computed above as -1, and x of 4 is given in the question as again -1. So this is 3 minus 1, which is 2. So 2. So the prediction error at n+1, that is at the 4th time instant, is 2. Anyone has any doubt? No doubt. Okay. So we proceed ahead. So this problem is also based on the about two problems, and we are basically asked the gain at K4. Okay, what is the gain at K4? So what is my gain? So what is the formula of gain? So Kn+1 is xn+1 rho n sigma square plus rho n x square n+1. Okay, this is the formula of gain in sequential estimation. Any doubts? Dr. S. Can you mute yourself? Sure. Yeah, thanks. So, right. So what? So K at 4, that is gain at 4th instant, will be x4 rho 3 divided by sigma square plus rho 3 into x square 4. Okay. So now let us see what we have. So now we are given that sigma square is 3 dB. So we need to convert the variance which is given in dB to watts. Okay. So how do we do that? So 10 log 10 sigma square in watts is basically 3 dB. So sigma square in watts is basically 10 to the power 3 by 10, and this is approximately 2. Okay, so you can use calculator for this. And next thing which we need is rho of 3. So this is sigma square divided by x transpose x. Okay, so this will be 2 divided by x transpose x, which is 3. Okay, so x transpose x we did in question 1. You can just refer that. So we have now rho at 3. Okay, so now we have all which we need to compute K4. So this is x of 4. X of 4 is -1 times 2 by 3 divided by sigma square is 2 plus 2 by 3 times -1 squared. Okay, and if we solve this, we get -2 by 3 divided by 2 plus 2 by 3, right? So this is basically 8 by 3, and this comes out to be -1 by 4. Any doubts in this question? No doubt. Right. So this is also following the previous three questions. And now in this question, they have asked the update, that is the quantity to be added to estimate h hat of 3, okay, to generate h hat of 4. So what quantity do we need to add to h hat of 3 such that h hat of 4 can be computed? So you need to remember this update equation, that is h hat of n plus 1 is h hat n plus kn plus 1 into en plus 1, right? This is the update equation which we have. And so here if you see, h hat of 4 will be h hat of 3 plus k4 p4, right? This is what we will have. So this is the quantity, right, to be added to h hat of 3 to compute h hat of 4. Are you getting this, right? So k4 times e4 is the quantity which you need to add to h hat of 3, right? You are going to add this quantity to h hat of 3 to get h hat of 4. So this is what the question is asking. So we need the value of k4 multiplied with e4, right? And what is k4? So k4 we had solved k4 in the previous step, right? So this is k4 is minus 1 by 4. This is minus 1 by 4 times e4. E4 was 2, which we computed two questions back. So this value is minus 1 by 2. So this value is minus 1 by 2. Any doubts? No question? Okay. So again, this question again follows the previous four questions, and we need to find out the variance of the estimate h hat 4. Okay, so we need to now compute the variance. Okay, so we'll again use the formula rho n plus 1, which is the variance update equation, and this is 1 minus kn plus 1 x of n plus 1 times rho of n, right? This is what we have. So rho of 4 will be 1 minus k4 x4 rho 3. Okay, so 1 minus, what is k4? So k4 is minus 1 by 4, which we computed earlier. X4 is given in the question as minus 1. And rho of 3, we computed as 2 by 3. Where did we compute rho? Here we computed rho of 3, right? We computed rho of 3 in this question. So we are going to use this rho of 3, right? And if we solve this, so we have 1 minus 1 by 4 times 2 by 3, right? And this is 4 minus 1 by 4, which is 3 by 4 times 2 by 3, so this is half. Okay, this is half. Any doubt? No, no doubts. Question 6. So in the context of estimation framework, okay, the PDF of the unknown parameter h, what is? So anyone wants to answer? Feel free. So for the so they have asked the question for the MMSE or the Bayesian framework. So what is the PDF of h called? So just recollect, what we just saw. Ph given y is py given h times p of h divided by p of y, right? This is the base rule. So what is p of h called? Anyone can answer. No. Okay, So I'll just again recollect this. So this is the base rule, right? So the a posterior is likelihood times the prior divided by some, this is for normalization. Okay. So P of H. So the PDF of the unknown parameter H, right, which they have asked, which is P of H, and this is called as the prior PDF, okay, prior density. Is it fine? Okay. Okay. The prior PDF signifies that the unknown parameter is what? So anyone wants to answer this? Manish, can you answer?
Sir, I think this is random.
It's random, correct? Yeah, it's random. Okay. In the context of the estimation framework, so this is again talking about the Bayesian estimation framework, right? The PDF of the unknown parameter on the observation y is termed to be so. Okay, so what is this? So this is basically asking the PDF of the unknown parameter conditioned on the observation P of H given y. So anyone wants to try this? Shailaja, are you there? You want to try this? KP, are you there? Manish, again, you want to answer?
Sir, this is a posterior density.
Right. So this is called the a posterior or posterior, right? So this is PS given y. So as per the question, you need to construct the PDF which has been asked. So this is probability of y given h times P of h or P of y, right? So this is the a posterior or also called posterior. Okay. So this is the posterior density. Okay. Right. The estimation framework described in the later set of lectures for which the parameters considered to be random. So what is the cost function? So we saw a cost function, right? So expectation of h hat y minus h squared, right? So this is my error, right? This is my mean, and we are, squaring it. So this is the mean squared error, right? So do we have something? Yeah, we have the mean squared error estimation, and we want to minimize it, right? So this is the MMSE estimate. Okay, this is called the minimum mean squared error estimate. Any doubts? Okay. And given the parameter h and observation y, the expression of MMSE. So this was what we computed finally, that h hat of y comes out to be expectation of h given y, right? That is, you have the posterior itself, uh, which is basically coming, and so this is given in here. Okay. So any doubts? Any other thing you want to discuss or clarify? Any other point? No? And I think that's all for today's class then. Right? So thank you.
Okay, thank you, sir. Thank you.
Yeah, thanks.